So our next speaker is Sergii Kadenko from Ukraine. And
right.
so do you see the number? There you are. You have the title. I don't have to read it.
Okay, sure.
Sergii, you go ahead.
Now from the top. Okay, so my presentation is prepared by a team of researchers from Kyiv, Ukraine. And in this current presentation, I'm going to describe an original rule for reduction of the number of pairwise comparisons in ISAHP. The research was initiated by my colleague Oleh Andriichuk and partly supported by NATO project Science for Peace and Security. I think I'll have to skip the outline because time is short and the presentation is also not very long. So a few introductory slides. As data is transferred from the minds of experts to the problem-specific knowledge base of a decision support system and then to the decision maker, its credibility may be compromised due to errors made during input and processing. As a result, the quality of recommendations provided by the decision support system to the decision maker is also reduced. And at the same time, when we are using ISAHP, we are usually dealing with the so-called weakly structured subject domains. They are influenced mostly by intangible factors, which are problematic to measure and formalize. So as Tom Sati showed, a handy way to get at least some analytical description of such domains is to compare the alternatives among themselves and then aggregate comparison data using decision support systems and methods. So based on this general consideration you all know about, I guess, we can conclude that there is a whole bunch of factors influencing the quality of recommendations submitted to the decision maker. And in order for these recommendations to be credible, we need to have sufficient volumes of expert data properly represented in the knowledge base of the decision support system and properly processed using adequate methods. But in this presentation, I will focus on improvement of recommendations quality during data input phase here. So Bill Wedley, in one of his papers, experimentally proved that through reduction of the number of comparisons, we might actually get better estimation results. By better, I mean closer to model values, if they are available, more consistent, and what's important, closer to the expert's own assumptions concerning the subject domain. In order to get a rating of n objects, we theoretically need to conduct at least n-1 independent pairwise comparison. According to Wedley's study, after this number is reached, consistency of the estimates first increases and then decreases. So we propose to take these considerations into account as well. Also, we suggest a specific order that should be followed when presenting pairs of objects to an expert for comparison. This specific order of pairwise comparisons, which was suggested by my colleague Oleh Andriichuk by Stevens and Galanter, they were dealing with tangible criteria such as length, time, and square. And they asked the respondents to estimate respect all three of these charts, the ground truth, that is the actual values brought to some unified scale, are located along the diagonals of the squares. And punctured lines represent the dependencies of direct expert estimates on actual values. On chart A, we can see the results of direct estimation of 17 evenly distributed lengths. The punctured curve has two similar convex fragments, 1 and 2. This means that estimates of lengths located at the ends and in the middle of the range seem to be the most accurate ones. On chart B, we see the results of direct estimation of 16 evenly distributed time intervals. The curve is convex along the whole range. This means that lengths of time intervals are generally overestimated, and the chart C is the most interesting one. The respondents directly estimated the squares of 9 rectangles. The rectangles were presented to respondents in different orders. Under sequence 1, the rectangles were sorted from smallest to largest. Under sequence 2, they were presented in random order. And under sequence 3, they were sorted from largest to smallest. These results, shown on C chart, indicate that respondents tend to overestimate the objects. However, this overestimation factor can be reduced if the objects are presented according to sequence 3, that is from largest to smallest. Now, the experiment of Stevens and Galanter featured direct estimates of objects according to the tangible criteria. So we try to extrapolate their results to pairwise comparisons of objects according to intangible criteria in order to be able to sort pairwise comparison values from largest to smallest, similarly to squares or lengths. First, we need to rank the alternatives of the objects. When the ranking is completed, we can present them to the expert for comparisons. First, we would ask the expert to compare the smallest one with the largest one, that is the most distant one in the ranking. Then we would present the alternatives whose position in the ranking differ by n-2, then by n-3, and so on. Thus, we will get n-1 turns of pairwise comparison series. And not all comparisons have to be performed, especially under large N. Under the listed assumptions, with each new turn, the significance of pairwise comparisons would decrease. So if we need to reduce the number of comparisons, it is better to skip the last turns from the list rather than the first ones. We tried to confirm the efficiency of the suggested rule experimentally. Each respondent was asked to consider himself competent in. After that, he was asked to formulate 5 to 7 criteria influencing this problem or goal, rank them, and compare them among themselves based on 3 different sequences of pairwise comparisons I mentioned above. Weights of criteria were calculated based on each pairwise comparison sequence, and respective priority charts were built. Each respondent was requested to select the chart he considered to be the most adequate one. That is, the chart that represented his beliefs concerning the chosen subject domains in the best way. Now, here is an example of a form where a respondent compares 5 criteria for office location selection. Criteria formulated by the respondent in this particular case include high ceiling for ventilation, infrastructure, a downtown proximity, square, and potential for space reorganization. And here, this is the form with the respective charts or histograms representing 3 different ratings of office location selection factors. The respondent is expected to rank the histograms according to their adequacy, that is, ability to reflect his beliefs concerning the importance of office location selection factors. First, we conducted a test set of 33 experiment instances. And then, based on this test set, we calculated the minimum number of experiment instances required to ensure statistical credibility of the overall results. So for probability 0.9, this number equals at least 67 instances. In this table, you can see the results of histogram rankings based on 67 instances of the experiment. Under sequence A, criteria were presented to respondents for comparisons according to the above-mentioned original rule, from largest to smallest difference. The respondent had to start with comparisons of the most distant factors in the ranking. And under sequence B, criteria were presented to respondents in random order. And sequence C is the opposite to sequence A. That is, the respondent has to start with comparisons of the neighboring criteria from the ranking and then so on and so forth. The original sequence A was ranked by the respondents as the first or the most adequate one in most cases, 43 out of 67. These empirical results, well, speaks in favor of the suggested pairwise comparison ordering rule. The main advantages of the suggested approach are presented on the slide. And we've suggested an original rule for ordering of pairwise comparisons, ensuring greater consistency and credibility of expert session results. This rule in its turn allows us also to devise an easy algorithm for pairwise comparison number reduction when necessary. In our view, these approaches will improve the HP algorithm and the credibility of resulting recommendations submitted to decision makers for each HP model case. This research was partly supported by NATO Science for Peace and Security program. And the main publications on the research can be found in our paper, also available on the conference website. And at this point, I would like to thank you for attention. Sorry for being too fast.
No, you weren't fast. You were just in time, I guess. Kind of hard to. So I personally don't have any questions. I was, when I first read this paper that you wrote, I was thinking that you know, Pat Harker had done research about how many judgments you need to get some sort of a stable eigenvector, right? Mm-hmm. And so not to produce all n of them. So it turns that when you have inconsistency, your eigenvector will take you away farther out from the scale. So if you do a 3 by 3 matrix and you only use judgments to be consistent, only use 2 judgments, you realize that you sometimes, by allowing yourself to be inconsistent, your eigenvector allows you to be sometimes more accurate because you can go beyond the 1 to 9 scale in the ratios. So that happened also in the big matrices. Well, the bigger the matrix, the more inconsistent you are. So reducing the number of judgments is important, I agree, but because it may cost you money, but at the same time, there are occasions in which people don't want to do that. So we did an experiment with it. It was a 10 by 10 matrix in a negotiation situation. And they started by doing, using decision lens, they used the off the main diagonal set of n-1 judgments. And they started that way, and as they got priorities, they realized they didn't like them. So they keep giving more judgments. And they end up producing all 45 judgments. And then when they got finally to the 45, I said, oh, now we like what you see. So you see what I'm saying is, it is important, sometimes it's costly. And there was another example I have from New York, a lady dealing with preparedness for situations like hurricanes and so on in the state of New York. And I said to her, well, maybe we should do spanning trees, right? Random spanning trees for each of the judgment for the.
Yes, sure. We do a lot of research in spanning trees.
Right. So then she said to me, no, I want to have all the judgments for all the experts. And she had 700 people. So I tried to get Decision Lens to work with them as a pro bono, whatever. There was no pro bono. They said it's too large, too many people. We don't want to do that. Too costly for the company to do it. So you can see. So I agree with you that sometimes you have to decide which situation you want to manage and how many judgments you really. Do you really have enough information? That's the question. And I don't have an answer for your question. I like what you're trying to do. I think it's very interesting.
Yes, and another limitation is that we do not have any specific accuracy measures when it comes to expert estimation. So this is the only approach to ask the experts whether they like the charts, the priorities they are getting based on this or that number of judgments. But this is also, I personally can say that it is also questionable whether we can trust the experts, whether they know what they are doing exactly when they select this or that.
To finish this, but there's a colleague who did a study about experts and how accurate they are based on their how confident they feel. And they turn out to be that the experts that feel most confident are always the most wrong, which is almost unbelievable, right? So that is part of what the psychological studies that have done with experts. So the people who
like Dunning-Kruger paradox, like that, something like that.
Yeah, something like that.
Mm-hmm.
So the question is, the person says, "Oh, I know for sure," and then they're wrong. And the ones who have a little bit of doubt, they say, "Well, not entirely sure," but these are the ones that are more accurate. So I'm not sure that that's always the case, but.
Yeah, this is Dunning-Kruger paradox, exactly.
Right, right.
It's always a question. The better experts you find, the better results you get. It's like that with expert methods, as always.
Right. Well, thank you.
Thanks for
Very
having
interesting project, Vitaliy. Okay, Oleh, I know you're there too.